So in the last lesson, we ran a random experiment where we rolled 2 die and recorded the face values of those 2 die. And then we defined a random variable as the sum of the face values on those 2 die. And what we're going to do in this lesson is basically just define some useful ways of representing random variables by the values that they can take and the probabilities of each of those values. And so we're going to write out the probability table for this particular random variable. X is the sum of the face values on 2 rolled dice, and that could be 1, 2, it can't be 1, it could be 2, 3, 4, 5, 6, it can be 7, it can be 8, and it can be every number from 2 up until 12. And each of these numbers, each of these sums on the face of the die, have a corresponding probability of occurring. And for the cases for 2 and 12, only 2 1s and only 2 6s will enable us to get a sum of the face values of the die of 2 and 12. And so there are 36 equally likely outcomes, and so the probabilities of these 2 events are 1 on 36. And we can go through. There are 2 combinations that give us 3, there are 3 combinations that give us 4, there are 4 combinations that give us 5 as the sum, there are 5 combinations that give us 6 as the sum, there are 6 that give us the combination of 7 as the sum, there are 5 that give 8, and we can just fill out this table like so. And in each case we're writing next to the value for x the corresponding probability of getting that value, and in this particular example, that is the number of combinations that give that sum divided by the total number of possible combinations. Okay, and if you want, you can go through and you can add up all those numbers on the top, all the numerators, and you'll see that they're equal to 36. And so if we sum together all these probabilities, we'll get 1, which is precisely what we want, because we want the sum of all the probabilities of all the different possible values for this random variable. We want the sum of all of those to be 1. And so we can write that down. These are all sum to 1 because we're working with probabilities. Okay, and what we've done here, where we've defined this relationship between the numbers, the different values that our random variable x can take, we've defined what we call a probability mass function. A probability mass function. And so a probability mass function gives, for particular values, masses of probabilities, big lumps of probability. And we can write this probability mass function as, we can either write this, the probability that x equals x, or the term we use for a probability mass function is actually this lowercase p. We subscript it with the random variable, and we put in x there. And so we could write, for example, that the probability mass function of the random variable x evaluated at 3 is going to be equal to the probability that x is equal to 3, and that's just 2 on 36. Or if we want to simplify, we can write 1 on 18. So the next thing we want to define is a cumulative distribution function. A cumulative distribution function. Cumulative distribution function. Otherwise known as just a distribution function. And this is going to be, I'm going to give it a special little bit of notation. It's going to be capital F. We're going to put a subscript capital X for the random variable name. And we're going to put in brackets little x. And we can read this as the probability that our random variable x takes a value less than or equal to little x. Okay. And so this is best explained with an example. So we can evaluate the cumulative distribution function for the random variable x evaluated at 3. And so this is just the probability that x is less than or equal to 3. If we look at our table, our probability mass table, we can see there's 2 possible values that x can take to be less than or equal to 3. It can take a value of 2, or it can take a value of 3. So the probability that x is less than or equal to 3 is just going to be the probability that's equal to 2 plus the probability that it's equal to 3. And we've already got a useful little bit of notation to describe that. So we could just write the probability mass function evaluated at 2 plus the probability mass function evaluated at 3, which is just going to be 1 on 36 plus 2 on 36 gives us 3 on 36. So if we've got a discrete random variable, we can summarize it with the table like this. And we can also describe it by its probability mass function, which maps each discrete value of that random variable to its corresponding probability. And we can also represent it by its cumulative distribution function, which tells us the probability that the random variable takes a value less than or equal to the particular variable.